All right. Hey, everybody. Welcome back. This is Kevin and Zach. We're going to do some live coding for you again. We've been chugging steadily through with some Rosetta Code problems, which is a great website where people post a bunch of different problems for computer science. And what's really fantastic is when we started doing this a couple weeks ago, there were about 329 problems that hadn't been solved in Mathematica and we're down to just over 200. So really proud of all you guys who have been going out there and who have been solving these problems. It's fantastic. I think people are having fun with this. So we're just going to keep doing it, just keep having fun. Zach, you want to say a couple words too?
It means that you covered everything. I'm excited to keep going. 100 problems were solved last week, so that's pretty crazy. But hopefully, there's still some problems that we can do.
Yeah. All right, let's get into it. I'm going to share my screen.
Let's stop our video. Okay.
Yeah. All right, so what we've got here on the left is this is just a list of the problems that haven't yet been solved in Mathematica. We went ahead and wrote up a way to import those links from the website into Mathematica. So we've got this long list of links, which I'm going to collapse down inside of there. And like I said, a lot of them have been solved. Look at that. We're already down to 219. And I think there were 329. So there's been like 110 of these problems, which have been solved mostly by you guys out in the audience, probably, I'm assuming. So that's fantastic. What we're going to do is take a random choice of these like we always do, and we're going to open it with the system. What we got, open it in my other tab. What we got here is something called humble numbers. Ooh, this sounds fun.
Humble
Humble numbers are,
number.
have you ever heard of a humble number, Zach?
No,
A
but
mouthful. You probably can't say that 10 times fast. I won't
they're
try, but
humble, so they don't want us to know they're there.
yeah, they have, okay, so it's positive integers with no prime factors greater than 7. That doesn't sound too bad. 7 smooth, highly composite. Okay, oh, okay. Yeah, so a humble number is only a product of 2s, 3s, 5s, and 7s. That makes sense. Or some power of those. Cool. Show the first 50 humble numbers. So it looks like they're kind of leading us to generate humble numbers using exponents. I'm going to kind of lean more towards actually testing numbers to see if they are humble or not, since I think Mathematica might be a little bit better suited for that. What do you think, Zach?
I think that'd be fun. Yeah, we could do that.
Yeah, let me just get organized here, create our little humble number section. Let's make it a hyperlink for posterity. Pretty neat. And collapse that down and we'll just start looking what we got. So the first thing is probably, let's get some numbers up here. Here's the first 50 integers. That's great. How do we select from these the ones that are humble? Well, first thing is finding out what the prime factors are, right?
So no prime factors greater than 7. Okay.
Yeah, it looks like prime factor isn't a function, but let's see. If I just search for prime factor, this is the documentation now. This is where we should always go. Always. Okay, great. Here's a list of the prime factors of the integer n. That's what this function factor integer does together with their exponents. Oh, great. Perfect. And it looks like it's sorted. Um, let's make sure that it's always sorted.
Mhm.
Um, so let's do a table of all the factors of primes going up to 120. Big list. And let's see. Let's see if it's all true that these are ordered. True. Okay. So what I confirmed was I looked at this documentation here and I saw that it ordered these from lowest to highest 2, 3, 5. This is going to be important because if we're just looking at the highest prime factor, it would be great if we could say last instead of saying something like largest. And I confirmed my suspicion. We can go to higher. by testing that it's all true, that factoring integers gives you an ordered list. Uh, so that's perfect. That's really good to know. And let's see if we factor all of these. So 1 factors into 1 with an exponent of 1, 2 factors into 2 with an exponent of 1, 3 is 3, but then 4 is 2 with an exponent of 2. Neat, that makes sense. And we're looking for ones which don't have any factor greater than 7. So we want let's test it. Let's find a number that does have a factor greater than 7, like maybe, oh, some big number. Oh, perfect. So this is not a humble number. It has a factor greater than 7.
Mhm.
What we want to do is maybe find the last prime factor. Okay, so it's 17 with an exponent of 1.
So we
So
need to
maybe the
show, okay,
first
so
one
we
I
need
have.
to show, so we want to find, we want to show all the humble numbers, which is somewhere, less than 23,562 because this has,
Right.
prime factor of 17.
Yeah, it's pretty big.
Okay, then we can do that. All right. So, and then we also want to express, do we want to express the number the way the output has it? Or what, is there like a way that they expect the output or they just want us to show the numbers?
Um, I think they just want us to show the number, but this is actually basically what factor integer is giving us.
Oh,
When we say
convenient.
factor integer of some number, it gives us 2 with an exponent of 4, 3 with an exponent of 1, 7 with an exponent of 2.
Oh, okay, all right.
And there might even be a way, I'm going to go down to the C also. Um,
Is the
so
integer exponent one?
the highest power of B that divides not really what I was thinking. Um, Maybe there isn't a function that does exactly what I'm thinking,
Thank you.
but
I
we could
see.
easily break it up.
We
I guess.
appreciate it. But you just said he likes the stream. He appreciates us solving
Oh,
problems. We
great,
appreciate
thanks.
the opportunity to, try to do these. So
Yeah,
glad
yeah,
glad
it's
you're enjoying it too.
glad that we're getting such good interactions too. All the people commenting are great.
So I guess so I understand because I wasn't aware of factor integer today. I was reading it. Um,
Mhm.
that is 2 to the fourth,
Yeah,
then 3 to the first, and then 7 to the second.
yields 2352. Yeah.
Okay.
So
Okay.
if I did, like you said, 2 to the fourth, I'm just gonna write it out because it's easy. It's 3 to the first and 7 to the tooth. That gives us the integer 2352. Yeah.
Okay. All right. I see. Okay then. We
Yeah.
can do this.
So what I have here is something that tests whether a number is a humble number, meaning that its greatest prime factor is greater than 7. So uh, this is testing that it's not a prime, or sorry, not a humble number. So we can make it the opposite, the conjugate, or whatever the logical term would be. And so this one isn't a humble number. Okay, great. Um, Maybe we could go ahead and just select from the first 100 number those that are humble. Now the hard part with this, uh, okay, so it skipped 11 because 11 is prime and 11 is greater than 7. Okay, that makes sense. Good. It seems to have worked. Um, Now the difficult part is, okay, show the first 50, right? We could just generate more than 50 and then select less than that. Like if we generate 500 and then select the first 50 of those, there they are. Um, Not the best way to do it, but it gets the job done, right?
Yeah. We can get there though. We can improve it, I think.
Yeah. Does this all make sense? Did I maybe go a little quick here? This we've talked about before, but if you're new to the language, can be pretty daunting at first. Basically what's going on is this little hashtag pound symbol is called slot in Mathematica. So if I go into the documentation, I just pull up slot, and this is a way to define a pure function. So if you have uh, some function with slots defined, and then you wrap it all up with this ampersand at the end, that's a pure function. So say I want to raise some number to its own power. This is that function, and I could apply it to 5, for example, and that's the same as 5 to the 5th.
What? So I guess for what you did, select range 500.
Yep.
You would this your last your last value of like your list is second list like 7 and 2. So is it checking for 7 or 2?
This list you're talking about? Or
No, like the factor integer list. It's a
oh,
nested list. Oh, so
right.
it's first line. Okay, I get it now.
Yeah, okay. This is a little confusing, I admit. So what I was going for there is when we factor an integer, we get some list. And what we want is whatever the last one is will be the greatest prime number that is a
Mm,
factor of it.
okay.
That's why I did this last. So that'll, for example, for this one, give us the list 7 comma 2.
Yeah.
But we're not interested in the exponent. We're just interested in the prime number itself. And so doing first after that gives us just the highest prime number that is a factor of this integer.
Okay.
It's written slightly different there. But then what we're checking is that the highest prime integer, which is a factor of this number, is less than or equal to 7, meaning that the integer is a humble number.
Okay.
And
So
then
there
this guy over here is a span. And this is essentially just picking out the elements 1 through 50. That's a little easier.
so there was a solution sent from the audience.
I don't know. Let
Um,
me pull that up.
so it's in the Zoom chat, so you can look at it. It's a
Great.
for loop. It's a for loop, and it gives every like humble number up until X number
Oh,
that we
cool.
have.
Uh-huh. Yeah, and so if that is correct, then if I plug in 10,000 here, it should give us the same list. So we've got a big list of humble numbers there generated by my method. Big list of humble numbers here generated by SG Huisman in
Yeah.
the chat, which is great. And let's just compare these two. So the output 55 should be the same as output 54. Let's see. True. Okay, so we've got two independent methods here that both generated the first humble, or the lowest humble numbers up to 10,000. Um, Fantastic. What we've got going on here is a lot, actually. Um, oh, this is pretty neat. Okay, so they went a little bit more of the generative method this way of generating humble numbers using these exponents.
Hmm. Cool.
Awesome. That's pretty great. Yeah, so just a way to show that there are usually more than one way to get to the same answer.
Oh wow. This okay. There's he made a
Oh,
test.
humble Q. Oh, that's neat. Yeah, so for a lot of the tests in Mathematica, like if you want to test that something is, say, an integer, it'll be in the form of integer Q. Um, I'm not super sure of what the Q stands for, query, question, something like that. But you're basically querying whether this is an integer. So 10 point is an integer, 10 is an integer. So
Wouldn't be
it's
doing. Wouldn't someone asked if Dylan Chapman asked if using for I guess our list we made, would it be
mhm.
easier to instead of using select range to just say from the range of all numbers from -1 to whatever number we could
uh,
produce? I think is what you're asking.
yeah,
Sure.
so if we, let me just pull up an example here. So here's a big factor integer. And instead of doing this slightly verbose first last type of thing that I did, the suggestion was to take first the last element and then the first element, which, yeah, exactly. This does the same exact thing. So this is part. The negative first is the same as the last part. In Mathematica, when you index through a list, you can go positive indexes, negative indexes, or even zero index. And the zero index is the so-called head of the list, which for a list is just head, or sorry, for a list is just list, my bad. So for example, if we indexed the list 1, 2, 3 at the ith position for I going from -3 to 3, and this is going through all the integers, we see that the negative third is the first, the negative second is the second, the negative first is the last, and the 0th element is the head list itself, which is pretty neat. So this is kind of a cyclical way that you can index into lists. I thought this is way better than a lot of other languages.
Oh, very cool. Um, do you want, so you have like a solution in mind, let's look at the task and uh, run what's it called? Like, let's go through what it's asking and let's try to produce it and then
Yeah.
go through our code and kind of see what's going on. And you
Yeah,
bring
so
a
actually try
very
to
good point,
do the
I
task.
see. There could be a nice humble number queue added to the function repository.
I
Maybe it
wonder if
will
there
come
is one.
along. He says there isn't currently one in the function repository,
Oh, okay.
but stay tuned, there may be.
Hey, Dan. Yeah, I don't see anything for humble, but yeah, I have found a lot of things that I've been trying to smash my head against the wall and just write it. Sometimes they've already been written up in the function repository because someone had the same issue that you had, you know? So it's a great
It's very
resource.
funny. These problems in what's it called? On Rosetta Code even have function repository like solutions doing them. So
Mm,
it's kind
yeah.
of interesting. There should be some sieve method to generate these numbers without the less or equal than max check.
Mm.
Um, you bring up a very good point, SWSH. I don't know. I wouldn't know exactly.
Yeah, there's
My whole repertoire is just like doing, iterative or, yeah, I've just got introduced to like mapping functions, which is supposedly different. And so, I would be interested to see it. Go
yeah,
ahead,
I would
Kevin. I'm
say that there's
sorry.
definitely kind of two methods that you could approach this with by either saying we'll take this form and we'll integrate it across I, J, K, and M to generate humble numbers, or the method we took, which is we'll look at all integers
Prevent it from
and
going
we'll
less.
select the ones which are humble. Um,
So
Difficulty with this is sorting them, in my opinion.
the
What were you gonna say?
discussion, there's a discussion that's like where if we iterate, we're afraid and we use our less than or equal to check that we might miss some,
Right.
and so that stuff like that.
Right. The difficulty with this is kind of getting them sorted.
Oh, I guess this makes more sense. I've never heard of this sieve thing. This is really
Oh,
cool. I'm sorry. Someone
this is a
someone just
sieve to generate prime numbers, right? Yeah. Watch this
I've
graphic. It's
never
pretty neat. Not
yeah.
that we're trying to, show off Wikipedia, but so
It's a
basically
cool graphic.
mhm. What this does is goes through and it gets rid of all the factors of 2, gets rid of all the factors of 3, gets rid of all the factors of 5, gets rid of all the factors of 7. So it generates prime numbers by looking for the smallest number that's not a factor of numbers that have came before.
Oh,
Yeah.
so that would be perfect. We would just do that and go up to 7.
Uh,
Would we?
yeah. You'd
I
have
don't
to
know.
go up to the 50th humble number, right?
Well, yeah, but I mean, if we just go up to 7 and make them all, then we can. Why stop at 50 when we could make them all?
Hmm.
I mean, I don't know. I don't know how we would implement this, so, feel free to chime in below, but, I would be intrigued.
I'll give a quick example of the generative method. I'm going to use a table which produces numbers of the form 2 to the I, 3 to the J, 5 to the K, and 7 to the M. Boy, that was a verbal challenge while I'm typing.
Will
Uh,
this will this iterate every one like 1, so it's gonna show you I, J, K, and M. Oh my
Uh,
gosh, that's a lot. All right,
yeah.
never mind. But you explain, because
So the issue that you can see right away is just how it's sorted. Um,
Mhm.
oh, I should have included 0 here. That makes sense. Yeah, is 1 a humble number? Actually a good question. What do you say, Zach? Is 1 a humble number?
Uh, wouldn't it just be all the numbers to the 0th? So theoretically, yes.
Yeah.
I don't
Well,
know.
they
One,
have to be, yeah,
one
greater
to
than or
me,
equal to.
one to me works pretty hard, and you don't hear a lot about one, so I think it's a humble number,
I'm going with it's pretty humble. Yeah. Yeah, so what we've got here is clearly not sorted. 1, 7, 49 up to 16,000 and then jumps down to 5. What we could do is just sort it. And then grab the lowest 50. So for example, there's our list and I'll grab the first 50. Oh, there appears to be a discrepancy. We've got one extra number here.
What is the so like
What are we missing?
so like what? There's too many numbers, or
It looks like 64. Yeah, 64 is included in my method up there, but
Mhm.
not in this method down here.
Oh,
Whoa. Oh, I know why. I only went up to powers of 5, and 64 is 2 to the 6th, right? So yeah,
yes.
if I go higher, it includes it. And there's one of the issues with using this generative method is
Mhm.
you're kind of guessing on these tolerances a little bit.
Yeah.
At least in the way that I've written it. I'm sure you could come up with a cleaner way where maybe you increase this first and then you increase that and then you increase that so you don't have to sort it after the fact. Um, but I think in the way that we've got it, these both do pretty similar stuff. And personally, I'm a little bit more happy with the selecting from a range, just so that you know that you have the
Yeah,
numbers
yeah.
less than 400.
That's what we realized. We only go to 5, so we
Yeah,
don't cover those powers that we need to cover.
yeah,
Very
exactly.
astute, though. We appreciate it.
All right, so
Yeah,
it
like
looks like we've got the first task done.
show the
That's
number of humble numbers that have X decimal digits. I don't know. I don't know what this is like asking, but
the number of humble numbers that have X decimal digits for all X's up to N inclusive. So it's as a function of N, I assume. Okay, I'm gonna go down and just look at what other people have done. So they got the first humble numbers, which appears to agree with us. That's great. So we definitely did that part right. Um, of the first N humble numbers, 9 have 1 digits. Oh,
oh, so
okay.
we're just counting the number of digits. Ah, so I was very confused when it said decimal digit. I'm like, aren't these integers? I'm so
You're right. Well, they have to say that
I had a real
otherwise, if it
yeah,
was base
I
2, base
realized
3.
that. Yeah, I
Mhm.
realized that. As you can see, I am a scientist who uses code, and so all of my code has like x's, f equals x,
Yeah,
and I use y and z over and over again, and temp forever. Very
yeah.
bad coding practice, but don't do what I do.
Oh, yeah. So I guess what we want to do is turn each of these into a number of how many digits it is. Is there a function that gives you how many digits are in a number?
Wouldn't
Yeah,
it just be
search
the length of the
digits.
digits? Integer digits. Yeah, that's it.
True.
That's the answer right there. It gives a list of the decimal digits in integer n. Wait,
Right. Yeah. So that was a list, and we could have done the length of the list, right? But I think
yeah.
this one here
Oh,
gives you
this
the
is
number
probably
of
just the
digits.
number. That's
Yeah. This
so.
gives.
Let's test it. Just
I might
count
not
a
be using
number.
this right, but digit count of 56 should be
Wow, that hurt.
that.
What is that?
Okay. There's
It's
1 5 and 1 6. Is that it?
okay,
Yeah, that's what it
but
is.
okay, that might be. What does
Which
the
I
integer
could
counts
total that,
do?
but
Yeah, what does the integers count do? I don't know what it does for sure. I just want to see it.
hold on. So what I'm seeing is with 1 input and 2 input, it gives this list of the numbers in that representation. But if we explicitly
Oh,
Hey, I don't know what D is.
Give the number of digits in, wait, type 2. Just put a 2 in and see what it does. Oh,
This would give
wait.
the number of twos probably, right? Which is 0.
Well,
So,
look at the second example.
right, this is the number of ones in a binary representation. So if we wrote this number in binary, there's 5 zeros and 7 ones, or the other way around maybe. Uh, wait, 5 ones and 7 zeros.
Okay. Yeah,
But
I
what we
think
could do is, so what this gives us is just the number
the chat
of
is
each of these digits,
recommending
right?
integer digits, or the chat is recommending the length of integer digits.
Right. Yeah, that would definitely work.
Why
So
don't we test digit count and integer digits, like for absolute timing, and see what it, try to run it
yeah,
over a list and see what runs faster.
yeah, that's a really good idea. So the two different things that we
They
have
probably
here,
run very quickly at the same
oops,
time.
I always got to spell length correctly. Why didn't that work?
You
Oh,
might have,
oh, my bad. I used digit count again. That's
that'll help.
yeah. Okay. So the two different methods we have here is this lists out um,
Oh, integer
each of the
length
digits.
too.
No,
Wait,
integer
someone
length.
recommended integer length too. I mean, we could just compare all three because I would be curious. Because we're gonna have to run these over, you know,
This
uh,
makes way more sense. Yeah.
we're gonna have to run this over like a list, so it would be good to know, which is
What's
the most
fastest?
efficient.
Right. So we've got three that each do the same thing here. What
I'm
I'm
just,
going to do is plot the absolute timing of this method.
do you want to do it over a list, or we're gonna just see what it does alone?
Yeah, yeah. And so what I'm going to do is discrete plot, which is a list. That's a good point. So I'll pull up discrete plots documentation. So this is basically the same thing as doing list plot of a table. You've got
Oh,
discrete plot of some number iterating.
oh, very cool.
Yeah. So we'll do digits from 5 to 1,000. Let's be risky. 2,700. We'll increasing by some prime number. There's a plot. And, and we'll do the same thing for this other method.
What is okay, well, it's very slow, so. Oh, we have a
Oh,
method without
this is
filtering.
way quicker.
Okay, we will test this too.
Yeah.
There's a method in chat for not filtering, like we are doing. I
Oh,
guess all
cool.
of the methods we've done.
Yeah.
I assume this is something to do with like the see. There's reap and do and so.
So from
Hmm.
my very involved testing here, it looks like the worst method was totaling the digit counts. That makes sense because this has to do conversion to different bases and then addition. The next best was finding the length of the digits, slightly less involved. And as is usually the case, the function which was designed for this purpose is the fastest. So that's generally what you're going to find is if there's a function that's made to do something in Mathematica, it's written extremely efficiently. And it just is always going to be the go-to if there's some built-in function. Just use the built-in function.
Mhm.
Yeah.
Okay.
Oh, that's actually a good point. So the integer digits of 0, this really matters because 0 isn't a humble number, um, is 0, and the length would give us 1. But if we did the integer length,
Integer's different is oh. So the
0
length of integer digits is different from integer length for 0.
for 0,
That's
and that
cool.
makes some sense, yeah.
Okay. So wait. Run the length of integer digits 0.
Yeah, this would be
It's gonna
1.
be 1, right? Yeah.
Yeah,
Okay, so
and
maybe it wouldn't be the best to use that. In this case, whatever. But if you're trying to, use it generally,
right. I guess
probably
what
don't
you'd
want to
have to
use that.
do if you want to be really precise with this is you'd have to remove zeros from the list and then do the length, which is just going to add time. So as we showed here, This one up there took 6 times 10 to the negative 7th. That's really short time, but this one did it in a third of the time. So we're just going to stick with integer length, and it's always accurate, even for the fringe cases.
Okay, cool.
Yeah.
All right.
Mhm.
Integer length is pretty fast and it does a good job. Try running this method without any filtering. Because I assume this is like the same philosophy as the sieve, I'm
Oh,
guessing.
okay, yeah. So we got some code in the chat here. Ooh. Okay, so this goes up to 1,000, and it says, whoa. Okay, cool. So this is what we're familiar with, and I'm going to convert that to standard form so it looks pretty. And what we're doing is, wow. So we've got a really big do loop here. Um, it's basically 4 nested do loops. This is neat. Yeah, it's just another way. This is great.
And there's no filtering in this. It's very cool.
Yeah, right. Exactly. You don't have to test the numbers. You know that they're accurate.
The
And
number, so every number this calculates is, every time it runs an iterative calculation, there is no question of like if it is correct or
right.
it is making a number. Okay, that's cool.
Yeah, great.
Well, thank you. That's pretty awesome. I didn't realize that was even possible. So, I mean, I guess
Yeah,
it is, but this feels eloquent.
yeah, fantastic. Right. Yeah, the upper bounds on each of these prime numbers exponents can go up
Uh,
to the maximum number that you could get to generate that number. So the maximum number that you could get to generate 1,000 from powers of 2 is log base 2 of 1,000.
okay.
Yeah,
And
neat.
then you sort it. So there's no gaps for any of the numbers. So it goes through every, way, every power of 2 to up to 1,000 that makes it. Then it goes through every power of 3 there. Okay. That's
Yeah.
cool.
All right, but let's get a little back on track with the problem. I still think I'm going to keep using this. Um, for one reason, it's the shortest character-wise, so easiest to read, kind of. What we want to do is get the number of digits in each of these. And we just found out through very extensive testing that integer length is the best function to do that. We've got a list of numbers that we want to apply integer length to. So we're going to use the map operator, which is a slash and then an at symbol. And what that did is it turned that list of integers into a list of the number of digits in those integers. Pretty neat. So we go to some crazy high number. We get all of those humble numbers and the number of digits in them. Or sorry, this is just the number of digits in all those humble numbers.
Oh,
And if we wanted to count up how many there are, something like count or bin or tally. Oh, I think there's something called tally.
so tally is okay. So tallies them element wise. All right, this is cool.
Very neat. Yeah. So what this is going to do is it's going to take this list of a bunch of ones, a bunch of twos, a bunch of threes, and it's going to say you've got 9 ones, 36 twos, 39 threes, 197 fours, etc. And there's more sixes. I just didn't go up to all of them. Neat. Okay. So what do we want to say? What do we want to say? I'm not really sure what n is. Why don't I just say like up to 7 or something? Um, so show as many as feasible or reasonable for above on separate lines. Okay. Um, so what I'm gonna do is just to get these in a slightly nicer form is cool. So I changed it into a list of rules such that it says there's 1 digits 9 times, 2 digits 36 times, 3 digits 95 times, and they want it in, oops, that's not how you spell column. and it just prints it out column-wise on separate lines they wanted it. So
Oh,
that's pretty neat.
so this is so this is how many numbers have one, how many numbers have
Hmm.
two. So do up to like what I mean do let's do a big number. Let's just do you know obscene number.
Uh, yeah, like, oh, a million.
Oh,
Think about it. Kind of cool.
you wanna test that running? Can we compare the absolute limit of the function without any filtering to the filter function? Like
Sure.
absolute
This guy
timing?
here.
Yeah, I would just be interested to see like is it faster? I mean, I guess theoretically yes, because you're doing less, but I have no idea.
Right. So I'll do it just up to 10 to the fifth here.
And then we'll run
Um,
ours and then we'll run the one we have and see what it does.
that was quick.
Okay,
Oops. That's my
much
bad.
faster.
Let's see.
And then,
Yes, absolutely. E. That is
well,
important.
this is probably gonna take a little longer because we're doing the column and the count.
Oh, that's a good point. Yeah, that's a good point. For this to be fair,
Yeah,
I want
I
everything to
just
be
want to, yeah, I
fair.
want to compare. I just want to see this. I'm pretty sure it'll probably be faster, but is it like
Mhm.
radically faster? But or is it like, you
Go up
know,
to 10 to the fifth here. Yeah, let's just compare the timing on these two. Oh, okay. This is a
much
lot
faster?
faster.
Okay.
Over an order of magnitude faster.
All right.
That's
I
pretty
mean,
neat.
I think that speaks for itself. I think we found the solution.
Yeah,
Thank you, Chad, for your help.
yeah, for sure. This is fantastic. So one thing I'm going to do is just have, oops, max be a local variable using width. So now max isn't stored anywhere once I do that at least. Uh, yeah, so this just holds max locally so that if we ever wanted to use it in a different cell, it wouldn't have this, this, yeah.
It does 10 to the 20th in 1 point. All right, yeah. Well,
No
I want to
way.
test this. I want to just do
No
10 to the
way.
20th. Probably.
This is gonna be such a big output. Hold on. All right, I'm gonna
Well,
suppress
just
the output.
yeah, just don't.
We'll see. Wow. Okay. That's crazy.
All right, we'll do the absolute timing of it.
Okay. You don't trust them?
I mean, I
Or
just
are
want to
we
see it. I mean, I just want to see it. Like, it's just cool. It's just
are
cool to
we
see the
comparing
number.
our machines now? Which machine's
No,
quicker?
no. I mean, we'll see. Oh,
Ooh,
that's really cool.
1.27. Pretty, yeah, pretty close to yours. Yeah,
That's pretty cool. Okay.
that
Well,
is
I think we
very neat.
found I think we found the right answer.
Yeah, definitely. So we could do, um,
Let's tally. Let's do the tally again on this
yeah.
and see what
So,
we're looking at.
oh yeah, yeah. So we just had someone ask what this ampersand means, and that is a great
Perfect.
question because it can be confusing. If you hover
Let's
over it,
show
it
Oh, I'm sorry. Go
yeah,
ahead.
you go.
I was gonna say let's show doing a reference and it not working because I think it's definitely like very illustrative when you use the ampersand when you're or you
Mhm.
don't use it when you need to use it and it doesn't work and you're like, oh, why doesn't it work? And then you
Yeah,
introduce the ampersand, you're like, oh, I get it.
yeah. So what the ampersand does is kind of says this is the end of a function. So if I define a function, here they have an example of number squared plus another number to the fourth. If I did a function that's a number raised to another number, I wanted to apply this to x and y. This wouldn't work without the ampersand. It's like, what the heck's going on? And that's because you need to close off your function definition with an ampersand, just to say everything before this, all those slots, all those pound symbols, those are inputs to the function. And the ampersand then says, okay, this whole guy's a function. So we could even say, um, this is some function, and then apply it to x and y. And there you go, it's x to the y. Or apply it to 2 to the third is the 8. Neat. So there is a really neat way to succinctly define pure functions in Mathematica. And it's super helpful when you're doing something like saying, oh man, I want to test whether some number has this property. All you need to do is just define a pure function where the input pound corresponds to the input instead of defining it with some sort of pattern sequence or something a little confusing like that.
Um,
Um,
what about using priority queue instead of sort? So reap and sort. I don't know what priority queue is. Maybe we can introduce it.
Priority queue. Did I spell Q right?
Yes, you
All
did.
the okay, good. Oh, it's a new data structure in 12.1.
I now use data structures instead of reap so most of the time. Okay. Well, I mean, we can
Oh,
try to make one. Let's try.
this
I mean,
fun. Yeah, if someone wants to look into this, definitely.
do
So
you
there's
think we can do it? I mean, it's all right because I'm very confused. By
yeah,
it. I would.
there's a lot of these data structures that are new, and I'm not super familiar with them yet. But it's great that we see a lot of people using them because they're made to be extremely efficient for what you're doing. So if you know that you have a list that you need to append to a bunch of times, there's a way to do that. It's like some immutable vector or something like that.
Can we try? Can we like try to make one maybe? Like let's try to make, I don't know. Let's try to make, a fast appending list or something and then try to
mm,
introduce our numbers here. I
so
mean,
try to do this.
yeah, maybe this might be too complicated. Maybe we want to take like a smaller, a
Mhm.
simpler process, but
Yeah, I mean, this is already pretty efficient.
it's super efficient. I mean, it'd just be kind of cool to see if we could try to use something new, or at least
Right.
try to use something new with it, because I didn't know about the data structure stuff. I didn't think I
So here's
saw it,
the
and I was like
things.
over my
Oh,
head.
okay. And it even tells you how quick it does things. So you can copy the structure in order n, drop them all, order n, turn a list of the elements, order n, order one to determine if it's empty, order one to define its length. Wow, that's impressive.
So
Length in order one. Each
okay,
returning element with the oh, order element with the highest priority is order one. That's pretty impressive too.
okay.
Log n for removing and returning the element with the highest. Okay. And X. Okay, so push. This is probably what you'd be doing instead of reap and sow. So what reap and sow do is you've got something that's sowing, kind of like harvesting seeds or whatever, and then that's going on inside this do loop, but you want to reap it outside of the do loop. So you're basically creating a table. It's basically the same as table. Um, I'd actually be interested if this is slower with table or quicker. Let's do some timing again. It seems to be the day to do a lot of timing. We're gonna be ballsy and just right off the bat do it with 10 to the 10. Okay, does it pretty quick the original way. Now if I change reap do sow into table, and I get rid of some of those closing brackets. Oh, it was slightly quicker. A little bit higher. Oh, okay. It's basically the same thing. So
Oh, well,
at least changing reap do so into table.
okay.
Yeah, roughly equivalent. So yeah, this is doing some big do operation which iterates across all four of these, sowing this number and then reaping it outside, as opposed to just creating a table by iterating across all of them. A little bit maybe more clear to read down here. So I'm just going to go ahead and keep using this version of it. And should we, let's try to get this whole showing them on separate lines. I think that's kind of cool. So if we want, we can do all digits up to 20. And then we'll tally them. like we did before. So this is 20-digit long integers. Big. And what I did before was ooh,
Is this gonna? Oh,
oh my goodness. That's not what I. Oh, my bad. My bad. Yeah. Okay. What I just did was created the whole list. Whoopsie. What I should have done was do integer length, like we talked about for a very long time. I completely forgot to use that new function that we talked about. And it looks like I'm still doing something wrong. So I'm going to back out here and at just look at this segment of the code. So after we tally, what's going wrong? Going further. Oh, I see. I see. Okay. This makes sense. So when I changed from reap do so, this was essentially doing table and flatten at the same time. When you do it with table, you get a nested bunch of lists, which is why we're getting all these weird lists sorted in there. So I need to do flatten afterwards, which may change those timings up there. I wonder. Um, oh, sorry.
we could just do stack or dynamic array, which has push. Dynamic array is faster for pushing, indeed, but you have to flatten the table. Okay.
Oh,
Would you like? We could try pushing.
yeah, so I'm guessing that pushing is the same as reaping.
It could be a push in the right direction. I'm sorry. Continue. Please continue.
It does
Okay.
look like we got the answer here. So there's one humble number with 1 digit, that's 1. 5 humble numbers with 2 digits, etc. There's 34 humble numbers with 20 digits. Whoa, who would have thought? Kind of crazy, actually. Um, yeah, so we actually just solved the problem. That is
Show as
fantastic.
many feasible, reasonable. Show all output on this page.
Let's do it. 10 to the
You want
40th.
to see all this output. I'm sure table will be faster as the size can be predicted before and is compiled.
Right.
Okay.
And
So
it,
I guess if I'm understanding this correctly, just so like kind of layman, dynamic array is good if you're working with something, you're not entirely sure how big your data is going to become or how much you're going to work with. Meanwhile, since we know theoretically when we start, we know how fast it's gonna or how much we're gonna how many data values we're gonna make. So table would end up being faster, if I understand correctly.
mhm.
So hopefully that's clear. If it's not, feel free to correct me.
Yeah, I think what you said was right, that table might be a little bit quicker because we know how far we're going up to. Also, in general, in Mathematica, um, you're probably going to be better off using things like table than things like do loops or for loops. I know that that's the type of thing that you learn in like any computer science class. It's like, okay, here's how you write a for
Oh,
loop.
we have a
But,
data. Someone made a data structure for us.
oh, very
Okay,
neat.
it's in the chat.
Okay,
Check it out.
very neat. What I'm trying here is also with table and with do, you can parallelize it, meaning you can launch parallel kernels. You can see the status of them, for example, right here. And so instead of using one kernel to try to do this 10 to the fourth number calculation, it's going to try to use all 6 of my local kernels to try to do it. And it might tell us how much time elapses on here too. Okay, cool. So to go to 10 to the 40th, it took us 5 seconds, 6 seconds, 10 seconds total, about 5 seconds on each core.
Pretty quick. Would expect
Yeah.
slower since table will be compiled. Oh my
hmm
gosh, you just right. That's so cool. Okay.
Yeah, I just iterated a I just iterated 4 numbers across some list up to 10 to the fourth. So pretty neat.
Very cool. Well,
Very
that's
neat.
exciting.
And this is the code segment that was given to us. Ah, cool. So we've got data structures going on here. So we created a data structure called priority queue, which I will pull up here so that you can read about it as I talk. Maybe that'll be good.
Scroll to top,
Yeah.
so we can read what it's all about.
Yeah. Okay. So then it does another do loop, a nested do loop with I, J, K, and M iterators. And what it does is it goes through each of those, it pushes this result to the data structure, and then at the end, we reverse it and we pop it out. Interesting. The one thing I'm not certain about is why we're using pop to go one by one instead of returning a list of the elements, ES elements. So I'm just going to try and see if that does the same thing. 1, 2, 3, 4, 5. Cool, cool, cool. Let's just try this instead. Risky business here. That's a different, yes. Ah, okay, it gave us the reversed order. So yeah, we need to reverse it because it goes biggest to lowest. Well, that didn't work, but if we sorted it, I bet it would work. Now that's going to take more time to sort. Um, as a lot of people know, sorting is kind of a complex thing. There's really good ways to do it. And there's really dumb ways to do it. It can depend on your structure. One of the dumb
Return
ways.
if it returns not sorted.
Can we talk about
Is
stupid
it?
sort, Zach?
Oh yeah, we can talk. So I think it's a fun function. Stupid sort.
Let's see if it comes in. Oh, good.
Stupid sort.
So
Perfect.
this is a
Let's
great repository piece.
let's just sort. Let's sort this data, but stupidly, and let's see what we're looking at.
Does
Uh,
that give me 100 random reels?
ooh, it said
No.
it gave you one random reel.
Oh, yeah. Yeah, my bad.
There's one random reel for you.
Oh, that's bad. My bad. 0 to 100, and we'll get 100 of those. And then it sorts it stupidly. So this just goes to show you what this one does is it uses repeated replacement and a condition. So we can actually probably copy this exact same thing and just do it. And what is going on here is what's going on here that symbol. So it's got some list and it will repeatedly replace until it can't replace any longer. Um, something which could be empty, something which has to be 1, something which has to be length 1, something which could be empty or any length. Given the condition that A is greater than B, it swaps the positions of A and B. So it goes through every single element and it swaps A and B if A is greater than B until you've got a sorted list. So this is about the worst way that you could do it. About. It's order n cubed log n. There's something that I've seen called BOGO sort, which just creates a random permutation until it guesses one correctly that's sorted. I think that one's probably a little bit worse, but basically the main point of all of that long spiel was that we've got a really good built-in function for sort, which instead of doing things stupidly, um, tries to
Ah,
do it the best way.
oh, well, that's very nice of it.
Yeah, and it can do things not just numbers, not just 1, 2, 3, 4. It can sort A, B, C, D, catfish, cat. It's
Very
almost
fun.
structured.
Okay. The whole point of priority queue is to get rid of sort, but you have to pop it one by one and still that's own and log
Okay,
in. Okay.
I see. So what we just
So
learned.
we're not sorting, but we have to do populate one. Okay, I get it. I
Mhm.
understand. I think I understand. I hope I understand.
Yeah. What was said was that instead of sorting this list, it's more efficient. Let's remember this number, 0.014, to pop each one out. It's actually roughly equivalent for this small number. Maybe if we went higher, like this would probably be pretty quick. 2.4 seconds, and that's with 10 to the 20th. Um, reverse it, DS elements. It is surprisingly taking somewhat less time. Oh, I'm not sorting it. That's my bad. Okay, so sort is still taking a decent amount of time, but the sort function that's built in, like I said, is incredibly robust. Um, and will actually sort these numbers sometimes quicker than doing things the hard way. Uh, that's what I like. You don't always have to do things the hard way, right? Does that make sense?
Yes.
Yeah, you can use, if you want something sorted, you just say sort instead of trying to have to do that yourself or create some weird repeated replace rule. Um, all right, I jacked up to 10 to the 40th here, so this is going to take quite some time. All right, that's probably the last calculation we have time for. We'll see if that, oh, okay. Took about 25 seconds there using sort. This might be quicker. We'll see. But as this runs, let me just wrap up, say thank you everyone for coming. This was a lot of fun again. We actually solved this problem, which I think is fantastic. So humble numbers, check. We went through a decent amount of trial and error. We acknowledged that there were a lot of different ways that we could generate these humble numbers, either by generating them the way that's suggested here, or by checking a bunch of different integers until we get the humble number. Um, we were able to see which method was fastest. So I was really happy that we were able to get that absolute timing and plotting of the timing in there. And just a lot of different techniques were suggested by people watching from home. Fantastic. Here's the solution. We went up to 40 digits. I'd be surprised if there's any other language.
They probably go as high as, reasonable. Here we go. Can we go higher? Let's just, what do they go to? And can we go higher? I'm sorry to
Go.
compete. Go, go.
Well, ah, okay. So this finished, and it turns out that sorting is actually quicker than popping. Um, wow, that's kind of crazy.
It
So
might be, it might just be a matter of the situation.
yeah, for sure, for sure. For example, sort is going to have an easier time with integers than it would with reals or with letters or something. Yeah.
Oh, we have something. You should upload the results of Rosetta Code. I ran 10 to the 75th.
10 to the 75th. That's great.
I don't know if Kevin, you want to upload this?
Yeah, yeah.
Yeah, definitely. He will
I'll
be
get something up
uploading
there.
it.
Yeah, I'll get something up there after we're done with this. Yeah, I think we've got the answer. So
Woo!
great. Thanks everyone for coming. Any final words, Zach?
No, thanks for all the help. I feel like I learned even more about the language, so I appreciate it.
Yeah, this was fantastic. Yeah, thanks for all the suggestions in the chat. and see you next week, hopefully.